Hello, guys. So today we're going to do, we are going to discuss a problem called N colors on a chessboard. Now, this is a problem which involves a lot of group theory and some amount of combinatorics. It's a combinatorics problem, and we're going to use group theory to solve the problem. And as you can see, we're going to use something called Burnside's lemma, which comes from group theory, but is a theorem of combinatorics. So this is a wedding, so to say, between combinatorics and group theory, which are two branches of mathematics. And we're going to solve the problem. Hope you like it. Let's start. Oops. Very sorry, just a second. Here we go. So the question is, how many distinct ways can you color a chessboard of 64 squares using 5 different colors? So we have a chessboard. Wait. We have, we have a chessboard. Oops. So I'm not drawing a 64 square chessboard. I'm rather drawing a 4 by 4 chessboard, which is the simplest I can possibly draw. And there are 4 cells, and each of these cells will have to be colored. We are in this case, we are 5 colors would be too many. So in this case, there would be 2 colors to say, and we have to use those 2 colors to color this chessboard. So how many possible ways can we color the chessboard using 2 colors? In the same way, our problem tells us that there are 64 squares in the chessboard, and we have 5 colors to color each and every cell. How many distinct colorings are possible, right? So basically, we have to find the number of distinct colorings. Let's see how we do that. So what do we need? We need a formal definition of a group, a non-formal definition of a group. We need to know something called a group action, and we'll use a visual approach to do that. And the third thing we need is a discussion on Burnside's lemma. We'll be proving Burnside's lemma, in fact. And that's how we do it. What is a group? Non-formal definition. A group is a set of actions which act on an object of some set X. I need to delete this first because otherwise it's going to look very peculiar. Yeah. So group is a set of actions which act on some object of some set X. So say a set X contains shapes, right? X contains a square, a circle, a triangle. So this is a set of objects, and say there's a group of actions A1, A2, ... where A1 does something called rotate by 90 degrees. And by rotate, we mean rotate anti-clockwise. So this square would be rotated. So the square has the corners 1, 2, 3, 4 as labels. On applying A1 from the group G, the resulting square would become 1, 2, 3, 4. Thus, the element A1 of group G acts on the square of set X. So this set of actions, this group of actions will act on the group of elements X, group of objects, set of objects X. Okay, the set X could be the group itself or any other set of objects. We'll come to that later. Let us first consider X as a set of objects, like a set of shapes or a set of 3D shapes or anything else, depending on what kind of action is appropriate for it. The actions of the group has some rules. Let's look at the rules. There's a predefined list of actions that never changes. Okay. For example, rotation around 90 degrees is a predefined rule, predefined action, and it is denoted by, say, A1, and it will remain A1 universally. It will never change. And the entire list A1, A2 up to AN, which contains the list of actions in the group, is fixed. It doesn't change. Every action is reversible, which means once an action has taken place on the group or on an element of set X, it can be reversed, which means the original configuration of that element can be retrieved by another action from the group G. So, for example, A1 takes this square from this this configuration to this. We need to get back to this configuration. How do we do that? We have another action which will rotate anti-clockwise, which will rotate clockwise by say A2, which will rotate by 270 degrees, right? So what happens here? We start at this configuration, right? 4, 1, 2, 3. If you apply a 270 rotation, one would come, well, a 90-degree rotation brings it here, a 180-degree rotation brings it here, a 270 degrees would bring it here. So one comes here, and if you study carefully, you'll realize that 2 comes here, 3 comes here, and 4 comes here. So we get back the original configuration of the square. In other words, A2 reverses the action of A1. So A1 is reversible. Every action is deterministic. Okay, this basically means that when a configuration is achieved on an object of set X by a set of actions of group G, that configuration can be achieved only by that set of actions of group G and not by any other set of actions, right? So again, I would like to tell you what it means. So for example, let's take this one only. So this configuration goes to this configuration using the action A1. This statement basically means that this second configuration can be achieved from the first configuration only by the action of A1 and not by any other action. That's basically what it means. There's no other action which can bring, say this is configuration A and this is configuration B. Then A1 goes to B via the action A1 alone, and there is no other element, say X or say Y in G, such that A can be brought to B using an action Y. This is not possible if unless Y is equal to A1. So this is the meaning of every action is deterministic. Okay. Any set of consecutive actions is also an action, okay? Which basically means action is a composition. We can have a composition of actions, basically. Thus, say for example, this particular example, this is say configuration A. It goes to this configuration using a rotation, a clockwise rotation by 90 degrees. And then you apply it again, or you apply say another one, which is say reflection, right? Which is a reflection around the say horizontal axis, a vertical axis. So, or a flip around the vertical axis. So this takes us to this. So this is B, this is C. So this composition of actions, A1 followed by A3, this takes A to C. What this sentence is saying is that this composition of actions is also an action of the group G, which means there is an action, say A4, there is an action A4 which will take this configuration A to configuration C, which is 1, 4, 2, 3. And what is that? Can you tell me what is that? Yes. So if you have a diagonal, a flip around the diagonal will take 4 right over here and 2 over here. So you see, that's the only interchange that has happened. 1 and 3 have remained where they are. Only 2 and 4 have interchanged. Thus, A4 is actually the flip around the left diagonal, right? So A4 is basically the composition of actions A1, A3. These are the 4 basic rules of a group.